Okay, for this discussion, I'll be covering 4 problems, all which involve flow field, vector velocity fields, etc. It's similar to the topic like the last 2 problems we covered last week, as well as what's covered in class last Thursday. So we're just gonna follow up on this topic and further delve into it. So this first problem here is similar to the problem from last week, which we ended off with. And here, I'll read the problem for us. It says, an idealized compressible flow has been proposed 3-dimensional velocity distribution given below here. So this is your velocity field, your vector field, and it details the x component of your velocity, notated as u, the y component of your velocity, notated as v, and the z component of your velocity, notated as w. So this is the velocity distribution given in this formula. We're interested in finding the appropriate form for function f of y to satisfy the continuity relations. So what we're interested in finding is the following function there, which is the y component of your velocity, v. So if we were to look at your final exam equation sheet, there's a section for the Navier-Stokes equation, the continuity equation, and the continuity equation is as following: time derivative of density plus the gradient dot product with rho times your velocity field is equal to 0. So back when we studied Reynolds transport theorem, we had the conservation of mass equation, where as integrals, looking at surface flux, changes in control volume, those terms. So that's the integral version of that. Now we have the differential version of that, and this is what the continuity equation is. Same principle, just different form. We're looking at derivatives now. 2 things to write down, which are our assumptions. We're going to assume steady state. Reason why is, look at our v equation, there's nothing related to time. There's no time involved. Like, no matter what point you are in your vector flow field, time is not a factor for determining velocity. The second assumption, which is given to us, is incompressible. And we'll get to, let's first start with steady state. Steady state means any time derivative is 0. So this first term here is 0. There's no change in density with respect to time. That term is going to get canceled out. We're just left with this dot product here. And this dot product is referred to as the convective term. And let's break it down. So if I were to break down this term here, it would be u times the derivative of your velocity vector with respect to x sorry. Sorry, please ignore this. This is a little earlier than I expected. So this form actually, breaks down to the following. It is the sum of all of your partial derivatives. That's what it is. So basically, derivative of u with respect to x component of velocity derived with respect to x, plus derivative of the y component of velocity with respect to y, plus the derivative of your z component of your velocity with respect to z. The summation of these terms and there's density here, I forgot to mention. The combination of these 3 terms, your partial derivatives, should equal 0. That is what it's saying. And with our incompressible assumption, density is constant no matter where you are in your velocity field. Therefore, we can factor all these rows outside of your derivatives. And if we divide both sides by rho, all the rows will get canceled out. Okay, so which then leaves us with the following equation: x derivative of the x component of velocity plus y component of velocity derived by y plus z component derived by z is equal to 0. Once again, quickly stating, before I cancel out the rho term, what I would see is density, kilograms per second, multiplied by the spatial derivative of of velocity. So this spatial derivative, cancels out the meters. Per cubic meter. So this is density. This is the derivative of any velocity forms. This will then get me the following form of kilograms per second per cubic meter, which is similar or analogous to mass flow rate in and out of unit volume. So similar to what we see with the mass flux with Reynolds transport theorem. But now this is the differential form version of it. Okay, so this is the formula for our conservation, our continuity equation relations for an incompressible flow field. Now, let's plug in our U, V, and W into this equation and solve for it. So for U, we look at x derivative of 4xy squared plus the y derivative of f of y, which we don't have yet, so we just keep it as is, plus the z derivative of w, which is negative zy squared, equals 0. So x derivative of 4xy squared, that gives me 4y squared. I keep the middle term. And my last term, z derivative of negative zy squared, gives me negative y squared equals 0. So everything here is in terms of y, which is, I guess, kind of nice. We're going to move everything over. We're going to move the y terms to the right-hand side. And then because this equation is a simple ordinary differential equation, we can solve via separation of variables, which I'll show right now. So derivative of fy is equal to 4y squared minus y squared is 3y squared. Move it over, negative 3y squared. I multiply both sides by the differential of y term, and I integrate both sides. This will then give me f of y is equal to negative y to the power of 3 plus some constant that is in terms of x, z, and or t. So this is the family function that would satisfy our incompressible flow field and the continuity equations. Any questions on this one? So this is a 3D problem, so it's harder to visualize. But last week the problem we did was 2D, and I think it's much easier to visualize with the contour plots and vector plots I showed in the notes. So that's in last week's recording. But if not, let's move on to the next problem. We're now looking at a converging nozzle. So I'll read the problem. But yeah, we're looking at a converging nozzle, and essentially we're only considering it based on one-dimensional velocity, or the velocity distribution in the x component, the x direction. So basically, any velocity that's normal to the surface of your nozzle, we're going to be ignoring for this problem. Just the velocity going directly down the nozzle itself. And that velocity distribution is representative by saying u is approximately the inlet velocity multiplied by this factor. This factor is 1 plus 2x over L. That's that factor. And once again, for 1D flow, the y and z component are both equal to 0. Schematic. And here's the given. Just one thing to note with the schematic is at the inlet, we notate that by x equals 0. Plug in 0 to our equation. U is approximately the inlet velocity, which is what, as I said, that's why we define it as v naught. That's inlet velocity. However, at the exit, when x is equal to L, plugging L into this equation gives us this factor is a factor of 3. So now we have 3 times our inlet velocity. So that's at the outlet, there's going to be 3 times the inlet velocity due to the geometric shape change of the cross-sectional area. So let's talk about the things we're interested in finding in this problem. So in this problem, we want to find general expression for fluid acceleration. So we want to find the acceleration formula. And then we want to solve for the magnitudes of acceleration given some arbitrary values at the inlet and exit. Okay, so earlier I was going on this kind of weird tangent, but it'll make sense now because I was thinking about the wrong section. So here's my solution. Acceleration. So in most cases, when we think of acceleration is the time derivative of velocity. And so this is also shown in your final equation sheet as well. But acceleration is equal to the time derivative of velocity per time. But in fluid mechanics, the reason why it's uppercase is we're referring to this as this is the material derivative of velocity with respect to time. And the material derivative is composed of 2 things. Material derivative has your typical time derivative of velocity. However, we also now got to factor in this convective term. The convective term is as following. U times the x derivative of your velocity field plus v times y derivative of your velocity field plus w times z derivative of your velocity flow field. This is your convective term. And the reason why this is important is as following. So let's talk about the time derivative, and in regards to this nozzle problem. When I start first pushing flow through the nozzle, the inlet of the nozzle doesn't have the initial, is not V naught. It's probably, sorry, 0 or something. So I start pushing flow through it so that inlet velocity goes from 0 to V. Yes?
Should that last term be VDW? Or is it all V?
All V's on top.
I see.
I'll explain that maybe in a bit. I'll try to explain that in a bit, but this is the formula. Yeah. So basically, all the component you're deriving will always be the V, but other stuff is like fixed in the equation. That's how I think about it. So obviously the inlet starts at 0, but you start pushing flow to the nozzle, that velocity at the inlet's gonna go from 0 and eventually it'll reach that V naught value. So that is time derivative. Over time, over time, the inlet velocity is going to obviously get to 0 or get to V naught, but it's going to take time. So there's some acceleration. But then when it steadies out and the velocity maintains at V naught, there's no more acceleration with respect to time in that regard, right? So that's why it's called steady state. The time derivative, or the difference in time does not matter anymore. So that's that first term. That's what we usually think of for acceleration. Change in speed over time. However, this convective term is important because now we're looking at control volumes and kind of like a fixed perspective. And what I mean by that is, in this nozzle, yes, we're at steady state. The inlet is at V naught, and your outlet is at 3 times V naught, right? That's fixed with respect to time. So over time, that's going to be the same values no matter what. However, as we move through the nozzle, which is kind of like a spatial difference or spatial acceleration, there is acceleration occurring in this nozzle because we know that it goes from V naught to 3 times V naught as you move through the nozzle. So that is another form of acceleration because you're moving to a different location. You're experiencing a different velocity. You're accelerating. However, over time, there is no change at that point. But you moving through the nozzle, there is some kind of acceleration occurring. That's that convective term. That's what it's referring to. It's kind of like a spatial acceleration. Acceleration due to you changing location in space. Rather than over time, there's change in velocity. Just something to think about as you go through these problems. Okay, with that out of the way, let's start breaking this down. So as you mentioned earlier with the velocity, this V dash thing, so you're deriving the velocity field. The velocity field itself, as you guys saw from last problem, that is a vector. It's composed of an x component, a y component, and a z component. That's what's being that's what's being derived. Each of these components is being derived and then multiplied by this u, v, or w term to kind of like determine or show where are you moving next in this flow field. So I guess nobody can just do this problem. So we're looking for the acceleration formula. We're told that this problem is one dimension, or 1D. We're given the x component for velocity. Therefore, most likely, we're going to look for the x component acceleration as well. So the x component acceleration can be written as following. This dv dt, look at just the x component, we get du dt, because u is the x component of velocity, plus u times du dx, plus v times du dy, plus w times du dz. As you see, all these u's and that are being, or all the terms, the only term being derived is the u, and these other terms are kind of like fixed. So here's our form. We're working in one-dimensional once again, and in 1D, we approximate v and w to be 0. Therefore, these last terms are going to cancel out because they're going to be 0. So our acceleration formula comes down to just two terms. Let's plug in u, which we're given, into both these terms. Ax is the time derivative of inlet velocity times 1 plus 2x over L, plus u, which is inlet velocity times 1 plus 2x over L, times the x derivative of inlet velocity times 1 plus 2x over L, So this is our formula written out. If I took the time derivative of my u component, there is no, as you see, our x component velocity has no relations to time. And as I said earlier, this means steady state, because obviously, initially, putting flow through the nozzle, there is change in velocity, but after a certain amount of time, it's going to steady state out for many systems, and it happens in this. So happens in this system too. No time variables in my x component velocity. Time derivative is going to give me 0. So I'm left with one term now. X derivative of this this component. There is the x term, 2x over L. That derivative with respect to x is going to give me 2L multiplied by my constant y naught. I'm going to get 2 u naught divided by L, sorry. That's my spatial derivative multiplied by u, which is u naught, 1 plus 2 times x over L. And that's ax. Ax is going to give me 2 u naught squared over L times 1 plus 2x over L. So this is the formula for acceleration in the x direction. That's part A. And part B, I'm not going to solve for this value at the inlet and at the outlet. At the inlet, once again, x equals 0. And I'll be substituting the values that are given in earlier in the statement. 2 times 10 feet per second, these are arbitrary, squared, divide by 6 inches, which is half a feet, divide by 0.5 feet, times 1 plus 0 over L, which is 0.5 feet once again. This term here gives me an acceleration of 2 times 100 divided by 1/2, which is approximately 400 feet per second squared. That's the acceleration experienced at the inlet. At the outlet, we plug in x equal to L. That's equal to 2 times 10 feet per second squared, divided by 0.5 feet, times 1 plus 2 times 0.5 feet, divided by 0.5 feet. Once again, as I mentioned earlier, this factor here turns into 3 at the outlet. So 3 times my acceleration at the inlet, that gives me acceleration of 1,200 feet per second squared. And that's how I'm able to derive, going through the material, starting from the material derivative of the vector field, the velocity field, to get acceleration. Then I get the acceleration formula for the x component. Then I plug in the values at the inlet and outlet to get the corresponding acceleration values of those two locations. That's how I go through this entire problem. Any questions about that? Yes.
Yeah, I was just, can you clarify why we can neglect the two convective terms in part A?
Yes. Once again, because we're looking at a 1D, one-dimensional velocity distribution.
Okay.
Basically, any velocity normal to the surface, we ignore. That's why it's 0.
All right, I got it.
Okay, yes. And just one thing to briefly mention is, in terms of BG units, speed of sound, which is A, is approximately, at STP, 1,100 feet per second. So given that acceleration at the outlet, you can, or what it feels like, is you can accelerate from 0, like from rest, to Mach speed within 1 second. That's that acceleration magnitude at the outlet. Okay. If there are no questions, I will now move to the next problem, which is actually similar to the first problem, but now it's 2-dimensional. So same converging nozzle, but now we're going to factor in y component. Still no z component though, so it's not 3D, it's 2D. So let me redraw a schematic. Here's my converging nozzle. So initially in 1D, we're looking at inlet flow, outlet flow, obviously. But that velocity is not normal to any surface. However, now with 2D flow, there is velocity that is following the surface of the nozzle to basically further highlight this converging nozzle picture in the flow field. This is how we expect the y component to react. It should be moving, following the walls of the converging nozzle. and that is given by the following formula. So we have modified our x component velocity u here, but we also have added the v component, which is here shown as negative u naught times y over L. So these two equations are what are given to us now. Okay, we're now gonna be solving for a few things. We're interested in finding, first, some streamlines within, like, in the flow field, and I'll talk more about that maybe in a bit. Streamline functions. We're also interested in finding the formula for horizontal and vertical acceleration. So, formulas for ax, ay. And finally, we want to find the largest resultant acceleration and its numerical value. Okay. So, maximum magnitude. So those are the three things we want to find. Just quickly, briefly speak about streamline functions. Essentially, once again, a streamline is like is like a given path in a flow field in which a particle is going to travel along that path. That's what a streamline is. Given a streamline, you're going to follow that path. And so in our case, as you see, like this flowing here, we expect streamlines to be following the curvature of the walls, or just following the going inlet to outlet. We shouldn't expect streamlines to be like curving around or anything, because that wouldn't be right in our converging nozzle case here. But we're trying to solve for a family of functions that can model like all the different paths in which a fluid particle can move from inlet to outlet. That's what the streamline functions are in this case. So let's start with part A. In, once again, final equation sheet, there's a section on flow patterns which gives you the streamline function, which is the first page. Streamline function for two-dimensional flow is as following. dx over u is equal to dy over v. Solving for this function will give you the family of, solving for this equation will give you a family of functions that correspond to the streamlines in the flow field. So we have u. U is u naught times 1 plus x over L is equal to dy over v, which is given as negative u naught y over L. Luckily for us, the u component is only in terms of x, and the y component is only in terms of y. Our variables are already separated, so we just got to integrate both sides. And because u naught's a constant, I'm going to cancel these out. If you notice this equation, if I did, u substitution, I can rewrite both these integrals in terms of du over dx, or over u, which is a form of ln of u. So I can convert these equations into ln's. So I would get ln 1 plus x over L. However, just note, if I derive this, I would get, due to chain rule, I would get this 1 over L. So there's going to be L out here as well. Is equal to L times ln, negative L times ln of y over L. And plus c, because this is a general integral. L's are constant, so I'm going to cancel this out. I'm going to iso the c terms. When we solve for streamlines, the c is usually referred to as psi. Psi is like the psi value is referred to, like, I guess, the streamline value. So for any given psi values, that psi value will give you the corresponding path over the entire flow field for one particle. So this streamline here is one psi value. This streamline here is another psi value, and up here another psi value. Every time you plug in a psi value, you're gonna get a different path, a different streamline that represents the flow pattern, or like the path of flow for a fluid particle, essentially. So all these values correspond to a different path. Our next up, let's isolate the c variable. I get ln 1 plus x over L plus ln y over L equal to psi. Due to log rules, a summation of logs is equal to a logarithmic product. So then I can get ln 1 plus x over L times y over L equal to psi. I'm going to e both sides, or take e to the power of on both sides. So a constant to the power of another constant is still a constant. And I get 1 plus x over L times y over L here. I want to isolate for y, kind of like I'm solving for like, if I ever plot, I'm like solving for y, so I can kind of like plot it in a way. I get y over L is equal to psi divided by 1 plus x over L. This is so basically what I've got here is a family of functions given different psi values in which I can plot streamline half values. And I have a plot here from the textbook. And what we see, and as you guys see, plugging different psi values or c values, we get the different paths going through the converging nozzle. And as you see, the flow is converging because we can assume like there's like a wall somewhere up here. But we do see the flow is converging through the nozzle, given these different psi values. The streamline paths do correspond to what we expect from the visual or the schematic. Any questions about part 1? Okay, if not, part 2. We've done this before, but let's go through it again. Acceleration is the material derivative of your flow field. The material derivative of your flow field is the time derivative, or which is also like the unsteady term, is also referred to as that, plus your convective term. U, derivative of flow field with respect to x, plus v, derivative of flow field with respect to y, plus w, derivative of flow field with respect to z. We're in a 2D problem, so our w term here gets canceled out. 2D problem, no z component. But with these 3 components, let's break them down into the horizontal and vertical components. Once again, this v is a vector of I, j, and k. So, ax is du with respect to t plus u du dx plus v du dy. Whereas ay is dv dt plus u dv dx plus v dv dy. We have we have these formulas given to us already. We're just gonna plug them in now. So dx is equal to the time derivative of u, which is u naught in the velocity, times 1 plus x over L, plus u, which is u naught 1 plus x over L, multiplied by the spatial derivative with respect to x, du 1 plus x over L. And this last term here is v times du dv. The y derivative of our x component velocity, u is in terms of only x, is not in terms of y. Therefore, that derivative would just give you 0. So just for time's sake, I'll put 0 here. Now for dy, or ay, we have time derivative of v. V is negative u naught y over L. Plus, so the x derivative of v, once again, similarly, v is only in terms of y. So x derivative will give you 0 plus v negative u naught y over L times the y derivative of negative u naught y over L. So I mean, obviously, same principle as with the x and y spatial derivatives. Both equations are not dependent on time either. It's steady state. Because it's not dependent on time, these time derivatives are also meaningless. Because there is no unsteady term. We're working with a steady problem. Okay, I want to simplify these accelerations. So x derivative of this term here, so x over L, that gives me 1 over L. Multiply by the constant u naught, I get u naught over L as the derivative, times u naught times 1 plus x over L, which is just u. And for ay, the derivative here is y over L. That derivative is just over negative u naught over L. That's my derivative side. Multiplied by v, negative u naught y over L. So ax, I get u naught squared over L times 1 plus x over L, and it's equal to u naught squared over L times y over L. So those are my formulas for horizontal acceleration and vertical acceleration. I'm gonna need probably one more page to finish this problem. Okay, speed this up real quick. So overall acceleration, looking at based on like to solve for the resultant vector, or similar, it's kind of, at least in this case, similar to Pythagoras theorem. It's square root of ax squared plus ay squared. I'm gonna plug in these terms. Both these terms share the same constant value. So I'm just gonna pull it out of the square root first. So this constant value is gonna stay the same, times square root of ax, which is 1 plus x over L squared, plus ay squared, which is y over L squared. The thing about y over L squared, though, is in part A, we have an equation that correlates y over L to x over L. So I'm now going to plug in this function to substitute in for y over L. U naught squared over L times square root of 1 plus x over L squared plus psi over 1 plus x over L squared. I'm going to combine, so in terms of acceleration, this is the formula for acceleration. The only part that's with respect to x is this part underneath the square root. So I'm going to look to find the maximum magnitude or maximum acceleration. I'm just going to focus on this term here. I'm going to combine this term into 1. So to do that, I'm going to multiply this side by 1 plus x over L squared. So I get 1 plus x over L to the power of 4 plus psi squared over 1 plus x over L squared. This is me combining these two terms. Based on the rules of, so to find maximums, essentially, you can, what's the word? You can take the derivative and set to 0, for example. That's what I wanted to do it. But what I'm going to do is do L'Hopital's rule. So I just basically take the derivative of the numerator and denominator and compare the two and see how they hold up. If I do L'Hopital's rule, this term will become a constant before this term, which implies basically that this term is growing, this term will as x approaches infinity, the numerator will also go to infinity as well. It's both gonna grow or be, I guess explode. That's how I think about it. It's both gonna explode at infinity. This means that as x gets larger, acceleration is also gonna get larger, or magnitude of acceleration will also get larger. Which means that maximum acceleration is gonna occur at the outlet rather than the inlet. Because inlet, x is 0, outlet, x is growing, getting larger. And as you saw from the last problem, this corresponds to what we saw at the outlet. Acceleration magnitude is like 3 times bigger than the inlet. And so once again, maximum acceleration magnitude occurs at outlet. Any questions on this process or anything I did here? Okay. If not, we have one last problem. And let's get started on that. So I think I briefly mentioned this during my first week, like going over the material. But here, we're considering a sphere of radius r immersed in a uniform flow stream, U naught. That's a schematic. So obviously, when you introduce this sphere geometry into the flow field, it's going to influence the flow, both upstream and downstream of the flow. And this influence due to the sphere can be represented by this theorem from chapter 8 that gives us the formula where the u component of velocity, or sorry, the x component of velocity u can be represented by the following function here, due to the influence of the sphere. This is the horizontal velocity now that the sphere is present in your flow field. And this is based on mathematical representation of what a sphere looks like and how and its influence in potential flow theory, which will be discussed probably, I'm not sure it'll be discussed in this class, but it maybe will be mentioned in this class. So yeah, obviously, we mathematically model the sphere, put into this flow field mathematically, and this is how the sphere influences the x component velocity. So what we're interested in finding is first, we want to find the location of maximum acceleration. And at least just for now, we're looking between 2 points upstream of the sphere. The first point is point A. Point A is 4 radius upstream from the center of the sphere, or I guess 3 radius upstream from the sphere itself. At this location, if I plug this x value into my formula here, I would see that the corresponding horizontal velocity at negative 4r is equal to 63 over 64 times the initial velocity of the free stream velocity. And this is like 98, 99% of the free stream, so it's basically the same thing as just the free stream itself. 3 R's upstream from the sphere surface. Point B is the surface of the sphere itself. Surface of the sphere, obviously, is x equals negative r. That's why I was saying we're 3 radiuses upstream from the sphere itself. At x equals negative r, if I plug this formula, or this value, into my formula, I would get that the corresponding velocity is 0. That is the stagnation point on the sphere. And this makes sense why we have a stagnation point on the sphere, is because velocity cannot just penetrate the sphere. It's going to go around it, obviously. So when the flow comes in contact with the sphere, it should stop when it comes into contact. It can't penetrate the sphere. That's why you have zero horizontal velocity at that location. We're going to get like y component and z component, of course, but not x at the sphere surface. Okay, anyways, and part B, we want to find the time it takes to traverse between location A and B. Those are the two things we're interested in this problem. Let's start with A. Once again, same theory, really, but I'm just going to skip it. You take material derivative, time derivative, plus convective derivative. In the end, you'll just get the following. Ax equal to time derivative of u plus u, x derivative of u plus v, y derivative of u plus v, or w, z derivative of u. Our u velocity given to us is only with respect to x. Therefore, any other term cancels out. And also we're 1D, which is also another thing. So, acceleration formula is u, so u naught times 1 plus r to the power of 3 over x to the power of 3 times the x derivative of u naught times 1 plus r to the power of 3 over x to the power of 3. X derivative of r to the power of 3 over x to the power of 3, that gives me negative 3 times r to the power of 3 divided by x to the power of 4. That's why I take the derivative, that's what happens. So the derivative, and I multiply the constant, u naught. So I get negative 3 u naught, r to the power of 3 times 1 over x to the power of 4. That's me deriving u, and that's multiplied by u. u naught times 1 plus r to the power of 3 divided by x to the power of 3. I'm going to take these parts as a constant out of the equation, but I want to factor this x into this term here. That's what I'm interested in doing. So when I do so, I get the following. Negative 3 u naught squared times r to the power of 3 times 1 over x to the power of 4 plus r to the power of 3 divided by x to the power of 7. So just doing factoring and distribution, that's all I'm doing right now. Now, that's my formula for acceleration in the x component. I want to find the maximum, so what I'm going to do to find maximum, I'm going to take the derivative, set it equal to 0 to find local mins and max. So dA of x, and with respect to x, because that's our only variable in this equation, is equal to, so I have my constant, obviously, x derivative of 1 over x to the power of 4, that gives me negative 4 divided by x to the power of 5, x derivative of r to the power of 3 over x to the power of 7, that gives me negative 7 r to the power of 3 divided by x to the power of 8 equals 0. The first part is a constant, so this part here must equal 0. I'm going to move the right term to the left side of the equation, sorry. So I get negative 4 over x to the power of 5 equals 7 r to the power of 3 divided by x to the power of 8. I'm going to multiply both sides by x to the power of 8. This gives me negative 4 x to the power of 3 equals 7 r to the power of 3. Isolating for x, I get x is the cubic root of negative 7 over 4 r to the power of 3. If I were to plug this into a calculator, what I would get is that x equals negative 1.205 rate r. So about 1.5 radius upstream from the center of the circle, or about 0.2 radius from the surface, upstream from the surface of the sphere. This is where the maximum deceleration will occur. And the reason I say maximum deceleration is because obviously at point A, we're coming in at some speed, the free stream speed. At point B, that's stagnation point, or no velocity. Therefore, we're expecting deceleration to occur due to the influence of the sphere. Deceleration is occurring upstream of the flow as the flow approaches the sphere. This is where the maximum deceleration occurs. Any questions on part A? Okay. So part B. We're interested in finding the time it takes to travel between point A and point B. Once again, final equation sheet, there's a section right underneath streamlines about path length, or I think path flow length, one of the two. But what that says is velocity is just change in location or change in space over time. So we can have like separation of variables to solve for change in time and change in location. Like you can get both these values by doing this. So in our case, u is u naught times 1 plus r to the power of 3 over x to the power of 3 equal to dx over dt. Separation of variables, I'm gonna move my du over and move this term over. Move my dt over and move any x terms to the x side. So I get du dt equal to dx over 1 plus r to the power of 3 divided by x to the power of 3. This left-hand side, also integrate both sides. My left side, if I integrate this, So one more thing I need to do is determine my bounds. So let's talk about the right-hand side first. In terms of location, I'm looking at the change in displacement from location A to location B. Location A is 4 radiuses upstream from the center of the circle. Location B is the surface of the sphere, which is negative r. So that's my bounds for the right-hand side. In regard to the left-hand side, I'm gonna take some arbitrary time, so t naught. And I want to look at the distance it takes to traverse between A and B, right? So therefore, I'm looking at t naught plus change in t. I'm going to evaluate the left-hand side first because it's easier. The derivative of u naught, because it's a constant with dt, just gives me u naught times t, which I then evaluate from t naught to t naught plus change in t, which gives me u naught times t naught plus change in t minus t naught. So I just get u naught times this change in t. That's the left side of the equation. If I evaluate a constant, I just get constant times the variable. The difference in those two is just t naught plus dt minus dt naught, so it's just time delta t. That's the left-hand side. It's simple. Left-hand side is right-hand side is a different story though. So here's how it works. I'm first gonna multiply both numerator and denominator by x to the power of 3 to simplify this integral. So if you look at this integral, there's currently no way to really solve it. You try different tricks, but most likely this is going to be too hard to solve. What you can do is this trick here. So what we're going to do is break this into two terms. We're going to have x to the power of 3 plus r to the power of 3, so that the numerators and denominators match. We can cancel out to be 1. However, to do this trick, we have to also subtract by r to the power of 3. So we have one term we can solve now, but we have another one we can't solve for, because once again, this is just 1. We can easily solve for that. So the second term here that we can't solve, we have to use the partial fraction decomposition trick to break it down into fractions or into parts that we can solve. So this is the next integral. Once again, this part is just 1 now. Minus. So it's 1 over 3r squared times x plus r minus x minus 2r over 3r squared times x squared minus rx plus r squared. So this we have 1, obviously, and this term here in the middle, 1 over 3r squared times x plus r, this is solvable because it's just log. If you do u substitution, it's just log. It will come out as a log of u. However, on this third term here, you can't really do that because the denominator, it's here. So if I do u substitution, let u equal x squared minus rx plus r squared. Du is going to be 2x minus r. So this is what we want. We want to match this term. However, our numerator is x minus 2r, so it says the coefficients are swapped. We want to match this in order to get this term into a log base integral. So what we have to do is one more partial fraction decomposition. And that will give us the following form. So first off, we have a curly bracket, 1 minus square bracket, 1 over 3r squared times x plus r, minus 1 over 3r squared times 2 times x squared minus xr plus r squared divided by 2x minus r, minus 3r over 2 times x squared minus rx plus r squared. And then I close square bracket, close curly bracket, dx. So now we have 4 terms, but all 4 terms are solvable. I mean, one is obviously just be u. These 2 are log-based terms. The 2 in the middle, there's a log-based term. And this last term, if you do completing the square method or perfect square method, you can get this answer in terms of a trigonometric function. It's one of the trig functions or inverse trig functions. So, evaluating each integrals, you should get the following: x minus r over 6 ln x plus r squared divided by 2. X squared minus rx plus r squared plus r over square root of 3 r tan 2x minus r divided by r squared root of 3, evaluated from negative 4r to negative r. That's what the right side of the integral comes out as. So yeah, it's pretty messy, it's pretty grueling, 100%. But here's the one thing just notice. If I plug in my upper bound, negative r, into this equation, what I want you to look at is this log term here. Negative r plus r, that gives me 0. So what I'm evaluating is ln of 0. ln of 0 gives me negative infinity. I also have one more negative coefficient out here. So negative of negative infinity gives me infinity. The change in time, or the time it'll take to go between point A and point B, is going to be infinity. This basically doesn't make any sense because, in real life, you would expect that the flow would eventually be able to come in contact with the surface and go around it. But once again, this is all based on a mathematical derivation of what a sphere should be in a flow field. This mathematical derivation is not, while it does basically, it does detail how the flow changes and moves around the sphere, it doesn't capture everything, especially moving to the stagnation point. It can't capture that physics. So that's why we have infinite amount of times for you to go between point A and point B. Any questions? If there are no questions, you're free to go. Thank you.